In this tutorial, we will be discussing VSPER structures. Lewis theory, in combination with the VSPER theory, which stands for valence shell electron pair repulsion, can be used to predict the shapes of the molecules. Let's take a minute to break down all those words, valence shell electron pair repulsion. Valence shell, that's the outermost electrons. Those are the electrons that are actually participating in the bonding. Electron pair meaning that either bonding electrons or lone pairs, one or the others. Notice that they were specifically referring to the valence shell, so we're talking about the electrons on the outermost that are participating in the bonding. Repelling, repulsion. Electrons are all negatively charged. Like charges repel each other. They're trying to get as far away from each other as possible. So valence shell electron pair repulsion really means the outermost electrons in their interactions and how they're trying to get as far away from each other as possible. To shorten it, we simply say VSPER. The VSPER theory is based on the idea that electron groups, lone pairs, single bonds, or multiple bonds, repel each other. They're trying to get as far away from each other as possible. This repulsion between the negative charges of electron groups on the central atom determines the geometry of the molecule. So we're just going to go through several of these so that way you can see how it matches up. Predict the shape of carbon dioxide in the Lewis structure CO2. So notice that the oxygens are on either side of the carbon. There's no other thing around here. The only thing is the groups here and a group here. So therefore it's going to try to get as far away from each other as possible. While the furthest distance from one another would be 180, a straight line. The geometry of CO2 is determined by the repulsion between the two electron groups, the two double bonds, on the central atom of the carbon. These electron groups get as far away from each other as possible, resulting in a bond angle of 180 degrees and a linear geometry of CO2. Linear is a straight line. Alright, so let's take a look at this one. We have 1, 2, 3 groups coming off that central atom. This molecule has 3 electron groups off the central atom. These electron groups get as far away from each other as possible once again, resulting in 120 degrees. If we divide all 360 degrees of a circle by 3, that's where we get 120. This is called trigonal planar geometry. Trigonal 3, 1, 2, 3. That's where the tri comes from. I've also actually heard this pronounced trigonal planar. I think it's typically called trigonal planar, but it depends on your instructor. I just want you to be aware of both pronunciations. Some instructors try to emphasize the tri part, so that way you realize it's 3. Planar means it's in a straight plane, like on a flat piece of paper. Now these bond angles predicted for H2CO are approximate. The CO double bond contains more electron density than the CH single bonds, resulting in a greater repulsion. Thus the HCH bond angle is actually 116 degrees. Let me show you what I mean. Alright, so if we look at these, there's more electron density up here. There's more electrons, so it's going to push the other ones down, thus making this angle down here, the bottom angle, actually smaller. Let's take a look at that again. Alright, so while we're doing this, if we have a lot of electron density here, it's going to push these down, making this angle here a little bit bigger, and thus pushing these together more, making this angle a little bit smaller. That's what this one is talking about. They're saying that The bottom angle there is 116, not 120, so it's a little bit smaller. So these are approximations here. If a molecule has 4 electron groups coming off the central atom, such as CH4 here, it's a tetrahedral geometry. Tetra 4. Okay, that kind of should be able to help you. If we took a sphere and looked at all the possible angles, 109.5 would be the most spread out all 4 of these could be. A tetrahedron is a geometric shape for 4 triangular faces. So we have a triangle here, one here, one at the bottom, and then one behind. The CH4 is shown as a ball and stick model. Ball and stick models are often used to clearly illustrate molecular geometries. So once again, there's a triangle here. There's a triangle here. There's one in the back, and then there's one on the bottom here. And that's where they get the name tetrahedron. The mutual repulsion of the 4 electron groups causes the tetrahedral shape. The tetrahedron allows the maximum separation among the 4 groups. When we write the structure for CH4 on paper, it may seem that the molecule is a square. The bond angle's of 90 degrees, but it's not. This is if it were in a sheet of paper. Remember, molecules are 3-dimensional. They can actually push out and pull in all 3 directions. In 3 dimensions, the 4 electron groups get as far away from each other as possible, forming the tetrahedron geometry. The NH3 molecule has 4 electron groups, even though it looks like it only has 3. It's because of this lone pair here. The lone pair is considered an electron group. We have 3 bonding and then 1 lone pair. You're looking for the amount of electron groups, not the amount of electron groups coming off that central atom. If you look at the electrons, the electron geometry, the geometrical arrangement of the electron groups is tetrahedral. Because of this lone pair right here, you still get those 4 triangles. The molecular geometry, the geometric arrangement of the atoms, is trigonal pyramidal. So it's based on tetrahedral, but then because that lone pair you don't actually see because it's not bonded to anything, it becomes a pyramid here. And this is trigonal pyramidal. Once again, I've heard some instructors try to emphasize the tri, so they'll call it trigonal pyramidal, but most people actually call it trigonal. The lone pair exists in influence on the bonding pairs. The bond angles for NH3 are actually a few degrees smaller than the ideal tetrahedral angles. The reason is, I know this is covered elsewhere, but I'm going to explain it right now. Those lone pairs actually are closer to the atom, so therefore it's closer to these, pushing them down a little bit more, thus making this here smaller. Okay, so let's look at water. H2O molecule has 4 electron groups. Once again, hydrogen, hydrogen, and then now we have 2 lone pairs again. If we look at the electrons, the electron geometry, the geometrical arrangement of the electron groups is tetrahedral again. Because if we count the lone pairs into it, we still get those 4 triangles. The molecular geometry, the geometrical arrangement of the atoms, is actually called bent. Because once we stop counting the lone pairs, because you don't actually see them in the molecule itself, but they still exist, they're still pushing down on those hydrogens. So that's why it's getting bent. It's not 180 degrees. The bond angle in water actually are a few degrees smaller than the tetrahedral angles. And that's because those lone pairs are pushing down against those hydrogens. Alright, so here's an overview of all the ones that you'll need to know. We have the electron geometry here. That's what if you were to have everything covered. For instance, tetrahedral, because there are originally 4 triangles on it. Notice that there's 4 groups. So this goes with this. Now, once we take the lone pairs into consideration, that's when we start looking at the molecular geometry. So notice when there are no lone pairs, it's the same. There's no lone pair, so it's the same. But once you start adding the lone pairs, then the trigonal planar becomes bent. With 1 lone pair for tetrahedral, it becomes trigonal pyramidal. With 2 lone pairs on the tetrahedral, it becomes bent. Alright, so to determine VSEPR, first thing you need to do is draw the Lewis structure. Then you need to determine the number of electron groups on the central atom. Then determine the number of bonding groups and the number of lone pairs around the central atom. And then you determine the geometry. Alright, so let's look at NH3. First thing we need to do is figure out the Lewis dot structure. So here's N, here's H. H has 1, N has 5. 1, 2, 3, 4, 5. So here's 5 electrons. Here's 3 times 1 for a total of 8 electrons. The least electronegative element, the most electropositive element, the one furthest away from nitrogen, goes in the middle. Hydrogen will never be in the middle. So here's nitrogen. We have 3 hydrogens surrounding it. Link the central to the peripheral. So that takes away 6 electrons. 2 electrons per line. So 2, 4, 6. I have 2 electrons left. Hydrogen can only be a duet. And so that is full because there's 2 electrons on a line. So there's 2 for the duet. So now let's look at nitrogen. 2, 4, 6. We need 2 more electrons to make the octet, and we have 2 electrons left. Works out nicely. So count the electrons, organize the atoms, and pair up the electrons. Now let's compare this to this chart. We have 4 things coming off. So it's going to have a tetrahedral arrangement. So it's going to be one of these 3. We have 1 lone pair, so therefore it's going to be trigonal pyramidal. Try this again. H2S. Count the electrons. 1, 2, 3, 4, 5, 6. Sulfur is 6. Hydrogen is 2 times 1. So that's a total of 8 electrons. Hydrogen will never be in the middle. So when we organize the atoms, sulfur will be in the middle with hydrogen on either side. Connect the central atom to the peripheral. Count up the electrons. We have 4. So we have 4 left. Hydrogen has a duet, so now we go to the central atom. 2, 4, 1, 2, 3, 4. There's our octet. Alright, so once again we have 1, 2, 3, 4 things coming off of it. So 4 groups puts us in the tetrahedral arrangement. From those 4 groups, we have 2 lone pairs. Therefore, it's going to be bent. Many chemists use the notation for bonds and to indicate 3-dimensional structures on 2-dimensional paper. They do this by saying that if it's right on the paper, it's going to be a straight line. If it's going into the paper, it's going to have a hashed line or a dashed line. And if it's coming out, it's going to have a wedge. The major molecular geometries used in our book are shown but here using this notation. Linear, they're both on the page. Trigonal trigonal planar, they're both on the page. Bent, they're both on the page. It's tetrahedral and trigonal pyramidal that are actually going to be an issue. They're trying to maximize the number that are actually in the page. So that's why we have two straight ones. Then we have the wedge and the hashed mark to go. The wedge is coming out towards us. The hash mark is actually going towards the computer screen. Same here. Here's in the plane. The wedge is coming out towards you. The hash mark is going into the computer screen. They really only do this once they get past 3 with a 3-dimensional structure. Alright, so the last one we're going to do is CO2. So carbon is 4, oxygen is 2 times 6 to make 12. We looked at the periodic table to determine this. Carbon's further away from fluorine, so it's going to be in the middle. Connect those. So we have 4 electrons used up. That gives us 8 electrons left. Oh, sorry. I forgot to add these 4. So we actually have 16 electrons total, minus 8. Minus 4 electrons from it being used up. So now we have 12 electrons left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now from here, we notice that the oxygens have a full octet. Carbon does not. It has 2 here and 2 here for a total of 4. If this oxygen shares its electron, we have this configuration right here. Alright, technically, that oxygen could probably share another one to have a single bond and a triple bond. But it seems more natural for the molecule to spread it out. So these electrons come over as well. So we have 2 double bonds. That's how CO2 gets 2 double bonds in it. Alright, so how many groups are actually coming off of carbon? We have an oxygen here and an oxygen here. There's no lone pair, so we only have 2 groups. So 2 electron groups gives us linear. No lone pairs gives us the molecular shape of linear. Let's take a look at those other molecules that we drew and see if we can put this NH3 into the dashed and wedged before we leave. So we have nitrogen in the middle with the lone pair. We have 3 things coming off of it. So you have a straight line for one, a wedge coming out for the other, and then a hashed line going in. And that's how you do the wedges in the hash lines to make it 3-dimensional. And that's how you use VSPER to determine the shape.